The next topic that we'll discuss is the fiber optic directional coupler. Okay, and this is basically a basic device which is the basis for many types of fiber optic components, like power splitters and combiners, wavelength division multiplexers and demultiplexers, optical filters, optical sensors, etc. Right? So we'll first study how the basic operational principle of a directional coupler and how they are used for these different types of applications. Okay, so basically the idea is you have two fibers, right? So there could be two different types of step index fibers, single mode fibers, or identical fibers, for example. Right? So what you do is you bring them close together. Okay, so over a region you sort of bring them close together. And over some particular length here, okay, you basically fuse the two fibers together. Okay, such that their cores now come very close to each other. Okay, so basically how this is done is, so in this region here, right? So for example, what you can do is like wind the two fibers around each other. Right. So of course this is sort of exaggerated, but they're sort of touching each other. So first what you do is strip off all the outer jacket and plastic covering, etc. And only the bare fiber is remaining, right? So you have the core and then a cladding, right? So typically the core for single mode fibers, let's say a few microns, right? 5 to 10 microns, let's say, and then the cladding around it would be around, so a typical number is 125 micron diameter for the cladding, okay? And then all the outer covering, plastic, jacket, etc. is removed. So you now have the cladding of the two fibers exposed to each other, okay? And then what you do is sort of you either using a flame or using some high power laser or something, basically you fuse these two fibers together. So the glass melts, right? And then flows into each other, and once you remove the flame or this high powered focus laser, then basically the glass solidifies again, and then now this whole thing has now become just one mass. Okay? So now this is fused to one mass. So now if I look at the cross section here in this region, right, so it looks something like this. So it's now one thing, and then you have two cores. Right, so the technologies developed that enough that you can control the spacing between the two cores very precisely, right, D, right? And of course, each core has some, so let's say this has some diameter 2A1 and this is 2A2. Right? So as I said, this could be similar or dissimilar fibers, right? So in this region, coupling region here, it looks as if you have a structure with two cores. Right? And now you can imagine, so what happens is that if you launch light from either of these two fibers, right, so they are separated, but once they come to this coupling region, you can imagine like, so now the mode profile here will leak. So let's say you have power launching one of the fibers, right? In this coupling region, now the intensity will leak into the region of the other core. Okay? So now the modes will be coupled in this region. Okay? And due to that, basically you can get some transfer of power from one fiber to the other. Okay, which is what we'll see how that mathematically works out. Okay, and then you can control various things like, for example, the spacing, the length of the coupling region, etc., and use it for useful applications. Okay, so these are known as fused couplers. So in this region, right? So basically, as I said, so basically it looks like you have two waveguides, right, close to each other. So again, this spacing is d, right? So another way to think about what's happening in this coupling region is let's say I launch light in one of the fibers here, right? So when the light arrives at the coupling region, it's mostly confined to this one waveguide, right? So the mode profile, let's say, looks something like that. For example, it could be the lowest order LP01 mode of this single fiber. Right? But for this structure here, right? So for this thing here, so this looks like a fiber with two poles, right? Right. So basically, the eigenmodes of propagation for this structure will look something like this. So they'll span both the poles, right? So if we, for example, if we want to find the exact modes for this kind of structure, we'll again have to solve the wave equation. But now we don't have sort of like cylindrical symmetry anymore. We have these two poles, right? So you can imagine like now, so the boundary conditions and the solutions will be different. But we can imagine what the solutions look like, right? So these two coupled waveguides, the situation is very similar to what you might have seen earlier in like different scenarios. For example, when you have coupled pendula, right? You have two pendulums which are, let's say, coupled to each other, right? So then we get to these two modes of oscillation, right? One is symmetric and one is anti-symmetric. Symmetric is when both of the pendula are oscillating in phase, right? Both of them are swinging together. And the anti-symmetric mode is when they are like opposite, right? They are opposite in phase. So when both go away and then both come together, right? So similar, and for example, you might have seen it in other places like, for example, if in quantum mechanics you have coupled quantum wells, then basically the energy levels of the individual wells sort of mix with each other, and you get new energy levels, and the wave functions again correspond to symmetric and anti-symmetric wave functions. Okay? So similar situation here. The modes for this superstructure with two poles, okay, can be thought of as a symmetric mode. Okay, so this is some psi s. So the mode profile will have a maxima in each pole. Okay, and for the symmetric mode, basically these two are in phase, right? So when there's a maximum here, there's a maximum here also. The other mode will be the anti-symmetric mode. Okay, so there these two will be out of phase. So when there's a maxima here, there will be a minima. So now we can think of the eigenmodes of this structure as the symmetric and anti-symmetric. Okay. So these are the invariant mode profiles for this structure with two poles. So for example, if we launch either of these modes, they will propagate without change, just like a mode in a waveguide. So now consider this light launched in this particular fiber here, right? So this you can see I can write as, so this input field here, I can write as a sum of the symmetric and anti-symmetric modes, right? Because, so when I add these two up, so in the top waveguide, these two will add up together, while in the bottom waveguide, these two are out of phase now, so they will cancel out, right? So when I add these two, I get only the power in only the top waveguide, which is my input. Okay, so I can think of the input as a superposition of this symmetric and anti-symmetric mode, right? And specifically, in phase superposition. Okay. And now you can imagine, so just like in any waveguide or fiber as we've seen, right? Different modes have different propagation constants, right? Depending on, again, sort of the boundary conditions to satisfy. Hello, can you hear me? Somebody says voice is breaking. Anyway, so right, so similarly here, so the propagation constant for the symmetric mode and the anti-symmetric mode, right, will not be equal in general, right? So they'll be slightly different from each other. So there's a difference in the propagation constant between the symmetric and anti-symmetric. Okay, so now you can see that, so if I launch some superposition of the symmetric and anti-symmetric modes, as they propagate, they acquire phases at different rates, right? So e to the I beta z, so betas are different, so there will be a phase difference acquired between these two modes as the field propagates, right? So you can imagine, like, after, let's say, some length here, so once I travel a length which is pi over delta beta, right? Where delta beta is the difference between this symmetric and anti-symmetric modes. The phase difference between the symmetric and anti-symmetric modes will become pi, right? So at the input they have the same phase, right? I've launched an input field which I can write as psi s plus psi a. So there is there is no phase difference between these two here in the input. But as it propagates, it acquires a phase difference due to different betas. And so let's say after a length pi over delta beta, you can imagine that there will be pi phase difference, right? So what that means is that now here, so after this length, I can write my mode profile as right, a superposition of the symmetric and anti-symmetric, but now with a phase difference pi, right? So this phase difference here is e to the I delta beta z, right? Depending on the propagations. So when that z becomes pi over delta beta, this will become pi, right? So this is basically, now I can write this as psi s minus psi. Right, and so what is psi s minus psi a now? So now I have to subtract this mode profile from this mode profile. So you can see that now the top waveguide, the field in the top waveguide will cancel out, and field in the bottom waveguide will add up because I do a minus. Right, so here at the output, now the field is in the other waveguide. Right, so you can see what's happening. So if I launch light in one of the waveguides in this coupling region, basically the power gets transferred to the other waveguide. Right, and if I increase the length here, then it will slowly get transferred back to the first waveguide and back and forth and so on. Okay, so now if I look at some half the distance here, then there will be powers in both the waveguides. Okay. Yeah, so hopefully the idea is now clear what's happening, right? And then you can imagine now, by controlling this separation and the length of the coupling region, I can control how much power is transferred, right? And then the coupling will also, you can imagine, depend on wavelength, etc. Right? So I can make different kinds of devices for different applications using this idea. Okay, so to treat this rigorously mathematically, what we do is use coupled mode theory, which is basically a theory for analyzing coupled waveguides like this. Right, so far in the course we just sort of looked at one individual waveguide or fiber in isolation. But so here we have two fibers in close proximity to each other. Right, so the situation can be thought of as, so So I have two individual okay, so let me call this fiber. This is 2, right? So this is the refractive index profile for fiber 1. Okay, so what? So let's say it's a step index fiber, right? So with some core radius A1, and there is some core and cladding index, right? So this will be the core index, and this will be the cladding index. Okay, so this is for fiber 1, and you can imagine, so for example, let's say the guided mode will have some profile like this. Right, so this I can, let's say I call it the mode profile is some psi1 of x comma. Right? So for example, this is the LP01 mode. Right, so and then I have the other fiber 2 here. Okay, so this distance is d by 2. Similarly, this distance is d by 2. Right, so d is the separation between the cores. So this is now the refractive index profile for the other fiber, right? And it will have its own mode profile like that. Okay. So when d is large, right? So before the coupling region here, right? So when the separation is large, these two are like acting like individual fibers. There is no interaction between the two, right? So one way to think of this is that basically this mode profile is decayed down to 0 by the time it comes to this other core. So when the separation is large, basically these are like two individual fibers and they have their own modes. So question is, both waveguides can be same parameters or can it be different? So as I said, they can be different, right? So for example, this fiber has a core radius A1, this fiber has a core radius A2, right? It could have a different core and cladding index difference, right? So in general, they could be different. No need for them to be. I mean, we look at a special case where both fibers are identical, but yeah, they don't need to. Right. So in the coupling region, basically the total refractive index profile, right, is now that, right? So again, this is B, right? So the total, this is the total refractive index profile n of x comma y. Right, so it's something like this case is sort of like a superposition of these two individual cases, right? So again, now, so in this case, for example, the mode profile may be like the symmetric mode, right, or the anti-symmetric mode. Right, so this now coupled structure has some mode profile psi xy. Okay. So basically, our task is to solve for. I mean, we are interested in this structure, right? Where so we want to see what happens in the coupling region. So we are interested in this structure, right? So we'll write it as some superposition of this structure plus this structure. Okay. So our task is to solve for this psi. We will write the psi in terms of the individual mode profiles in the two fibers. Okay. So if you just look at these individual fibers when they are not coupled to each other, right? So they satisfy the wave equation. So recall this is how we solved for the modes, right? So in this case, the mode profile psi1 satisfies the wave equation okay. So it satisfies, so this is the transverse part of the del square operator, right? So the cross-sectional coordinates xy. Z is the propagation direction, right? So we call this how we solve for the modes, right? So here I have written in Cartesian coordinates, right? But for example, for fibers we use cylindrical coordinates. But the idea is, so this is the equation, right? The wave equation that we solve for. So the solution to this, when the refractive index profile just consists of n1, just the fiber 1, then the solution is the mode profile is I1, right? With propagation constant beta. Right. Similarly here, when I just have fiber 2, the solution to the wave equation is the mode profile in the fiber 2, side 2. Right. So now again, these two fibers could have different properties, so psi1 and psi2 could be different, right? For example, they could be LP01 modes for the respective fibers, but the exact field profile could be different if the core size or the core cladding index differently. Right. So now for this superstructure, also the total mode profile that we're looking for will solve the wave equation, right? Okay. So let me start from the the homogeneous wave equation, right? Like this. And then we put some this mode profile as, so we have some intensity profile or the field profile in the xy direction, and then in the z direction we just take right. So this k0 square n square comes from the, we call it comes from e to the I omega t, right? So I guess we start from here, right? Right. And then we take e to the I omega t minus beta z. So the omega t gives me k0 square, because a double derivative of time here gives me omega square. And then omega square by c square, I write as k0, right? And then for the spatial part, if I write the mode profile as some cross-sectional field profile times a phase in the z direction, then when I plug this in, so the z part gives me this beta square, right? So that's how we end up with this equation. So so for the superstructure, let's go back to this equation here. We'll see the reason for that, why we directly don't go to this equation first. Okay, so this mode profile here for the coupled structure, now we'll solve this equation here. Okay, and so we know, so because we know the parameters of fiber 1 and 2, we know the mode profiles psi1 and psi2, right? We've seen how to do that already, right? So basically, since we already know psi1 and psi2, if we can express this total mode here in the coupled region in terms of psi1 and psi2, then we can write the mode in the coupled region, right? So basically what we do is, right, so write the mode here, total mode, as a sum of or a superposition of the two modes. Right, so the mode in the first fiber is sine 1 times e to the minus I beta 1 z, right? Because we put the propagation constant e to the beta 1, right? So we put a coefficient A of z to that, okay? And then the other field in the second fiber, psi 2 times e to the minus I beta 2 z, has propagation constant beta 2. We add that with a coefficient B of z. Okay, so now we have made a superposition of these two modes where the amplitudes are a function of propagation distance, right? So why we do that? We sort of already discussed, right? So this in terms of this symmetric and anti-symmetric modes, right? So in general, if we launch some input field profile, we see that power gets coupled between 1 and 2, right? So basically, the coefficient here will give me the power in waveguide 1 or 2, right? So now that becomes a function of propagation distance, right? Because of this coupling and the phase difference between the symmetric and anti-symmetric, right? We saw this transfer of power happening. So the coefficients here are now Z divided. Okay? So we can write this superposition sort of under the assumption that the waveguides are not interacting very strongly. Right, so the separation between the waveguides here, sort of we can say is bigger than the wavelength, okay, or it's also bigger than the core size, right? So basically, so you can imagine the amount of field sort of leaking here. So if we take the mode profile in one of them, the amount it leaks into the other fiber, this amount is very small. Okay? So that you can imagine will happen. So if D is bigger than the core, because again the mode is sort of well confined, at least the fundamental mode is quite well confined into the core, right? So we can write this total mode as a linear combination of these two individual modes under this assumption. Okay. So if they are so close that, you know, for example, like right, so the separation is of the order or smaller than the core size itself, then you can imagine now like this will have its own modes which are sort of very different from the individual modes, because now they are so close together, right? So you almost cannot think of them as two different fibers close to each other. It's like a new fiber with this new refractive index exposure. Okay. So in that case, for if D is of the order or smaller than A or the wavelength, then basically you have to solve for this equation exactly with the boundary conditions for this superstructure. Okay. But for most applications for fiber optic devices, basically we work in this regime, right? Because that allows us to design the device for our application, right? So in the weakly coupling regime, we can write the total mode as this linear combination. Okay, so basically now the task is simple. We need to find these coefficients A and B. So if we find these coefficients A and B as a function of distance, then we know what's happening in the coupling, right? As a function of distance. So how do we do that? So now we substitute this mode profile into the variables, right? So we can just go ahead and do that. Okay, so yeah, we'll just plug this thing into the wave equation here. So okay, so this first term here. So del square. So now this is the transverse part plus the uh, in the propagation direction, the derivative in the propagation direction, right? So we get the transverse. So for this, you get the transverse part, and then the z derivative gives me beta 1 square, right? And then I have this term. Right? Similarly, now for the second term here. Right? Right. So this is we took the derivative of this part, but you can see A and B are also z dependent. Right. So this del by del z, right? So I'll get more terms. Okay, so I have a double derivative with z here, right? So you can see the z dependent terms are a of z and then e to the I beta z here, right? So if both derivatives act on this, then I get the beta square term, right? Now both the derivatives could act on a, then I'll get a d square a by dz square term, right? Or d square b by dz square term, but we neglect those terms. Okay, so we neglect the double derivative of the amplitudes in relation to this cross term, right? So the other term would be so one time the derivative one acts on a and then one acts on this exponential term. That is what you get here. So you get the I beta out front and then dA by dz. So basically we say that this double derivative term, the magnitude is much smaller than this. Basically the magnitude of beta times the first derivative. Okay, so this is known as the slowly varying amplitude approximation. Right, again, it works well for this limit of weakly interacting waveguides. Right, so you can imagine because the coupling is not very strong, this A and B won't change very fast, right? At least compared to a wavelength. Right, so beta, recall, is the propagation constant, so I can write that as 2 pi over lambda times n effective, right? So this is like how much this slope dA by dz is changing over one wavelength, right? So this is 1 over lambda here, right? So basically this is how fast the slope is changing, right? And so if I take the lambda here, right, I'm saying like how much the slope is changing over a scale of one wavelength. Okay, and that we say is very small compared to the actual square, right? So which means, or the fractional change in the amplitude or the rate of change of the amplitude over one wavelength distance is very small, which is sort of another way of saying that the waveguides are not strongly coupled, right? So the power is getting transferred between the two, but that's happening over length scales which are much bigger than the wavelength. Okay, so the slowly varying amplitude approximation comes across. You come across it in various different places in optics. Okay? So it works in various different places where the amplitude is not varying too fast, which is most of the cases, apart from few rare. Okay, so we neglect the second derivative of these amplitudes. So then we are left with these terms. Okay. So now you can simplify these a bit more. So you can see that, so we have psi1 satisfies this equation, right, with n1. And now here we have, it looks like a similar equation, except just we have the total n here, right, which includes both the fibers instead of n1. Right, so this equation is the same as this equation, except n1 has been replaced by n. Okay, so I can add and subtract this k naught n1 square here, right? So then the k naught n1 square with these terms will just become 0, right? And the only thing remaining will be k naught n square minus n1 square. That will be what this thing reduces to. Similarly, this thing will reduce to just k naught square n square minus n2 square. Okay, so I can write the equations like this. Okay, so yeah, so here, right, so as I said, so this, I'll just be left with k naught square n square minus n1 square, so that I write as delta n1 square. Okay, so here delta right, so recall what this delta n12 will look like. So the total, this one looks like this, right? And from that I subtract, let's say n1, so I subtract this, right? So this will go away. So delta n1 square will just be, so it will be 0 everywhere except in the second fiber region. Right? And similarly, delta n2 square will look right? So this is like a perturbation. So this delta n1 square is like a perturbation which has been added to the first waveguide, right? And delta n2 square is a perturbation which has been added to the second waveguide, the refractive index profile for the first wave. Okay? And delta beta here is basically beta 1 minus beta 2. So we just so we multiply the whole thing by e to the I beta 1z. So this with ones the phase factors go away, and with the twos we get delta beta. Okay. So that's the difference in the propagation constants of the bare modes in fibers 1 and 2. Okay. So again, now recall that our task is to solve for A and B. So we basically want finally equations in terms of for A and B. Okay. So now we can use, for example, the properties of the mode profiles like orthonormality, etc., right, to simplify this equation. So, for example, if you multiply by psi1 conjugate, the mode profile of this fiber 1, and then integrate over the cross section. Right, so here, so we are multiplying by psi1 star and integrating over cross section. So wherever I have psi1, so here I have psi1. So here I'll get integral of psi1 star psi1 dx dy. Right? So that's like the intensity integrated over the cross section. Right? Similarly here. And then I'll get some cross terms. Psi1 star psi2. Okay. So I can write this like this, okay, where kappa 1 1 okay, right? So I get so from this term I'll get a, so recall delta n1 square is also a function of xy in general. So that was the, we just saw the perturbation, right? So delta n1 square is in the region of the second fiber, right? So psi1 star I multiply by here, so I get psi1 star delta n1 square psi1, integral of that over the cross section, right? So recall, so what this term would be, right? So delta n1 square, recall, is like this in the region of fiber 2, right? And psi1 looks like this, recall. Right? Psi1 is the mode profile in fiber 1. So basically what we are doing is multiplying, so here psi1 with this delta n, right? So basically the only part contributing is this small part here. Right, and we divide by the mod psi1 square dx dy coming from here. Right, so here we have a psi1, so psi1 star, so that will be, so this is the normalized power, right? So for example, we can normalize this to 1. Right, so you can see that this coefficient k1 kappa 1 1 is just depending on how much the mode of one fiber is leaking into the region of the other. Right? So basically this kappa on one will be smaller and smaller as the separation increases, right? Right? And then this cross coupling kappa 1, 2 Okay, so now that you will see that out from the cross term here, right? So that depends on, so here xi1 star delta n2 square xi2, right? So what is that? So psi1 star, so psi1 like that, then delta n2 square, right? So actually delta n2 square is in the region of 1 as we saw, right? And then multiplied by psi2. Right, so it's the product of this and this and this. So you can see that the contribution here from the mode profile 1 is significant. Right, so for kappa 1, 1, basically we were looking at both contributions from 1 in the region of 2. Whereas for this, the cross coupling, right, the cross coupling which couples the term A and B, that depends on basically the product of these two wave functions, which so how much one leaks into the other times its own wave function. So you can see that this term will be larger. Right? So this cross coupling term will be more significant compared to this. Okay, and then we neglect one, so you can see that we would have had one more term here from here, right? Which will be integral of psi1 star psi2. Right? So basically we neglect that term, so we say that psi1 star psi2, the cross product of the mode profiles is much smaller than the self product or the intensity. Right, so we would have got another term if we took that, which would have gone something like integral of psi1 star psi2 divided by this mod psi1 star, but we say that is small y because again, so what is psi1 star psi2? That's a product of these two, right? So but that's when one is high, the other is low, right? So the product of these two, when this is high, this is actually low, and when this is high, this is low. So the product integral of that will be very small compared to if I just take the square of one of them and integrate. Right? So we assume that and neglect this term. Okay, so then we have an equation for A here. So now we say that A and B are coupled, right? Similarly, you can do the same thing, right? So multiply by psi2 star and integrate over the xy plane. So then we'll get an equation for B similarly, right? Right, so if you do that, and similarly we get equation for B. Okay, so now basically just 1 are replaced by 2, so kappa 2, 2. Right, so now this will be how much intensity of the mode in fiber 2 goes into the region where the fiber 1 is. Delta into square, again recall, was where the fiber 1 is. Right, so for identical fibers, of course, kappa 11 and kappa 22 will be the same. And similarly, the cross coupling term here. Right, so using these expressions, we can actually calculate what these coupling coefficients are. Right, so if you know the mode profiles psi1 and psi2 in the bare, right? So these could be, for example, fibers, or these could also be some other types of waveguides. Right, for example, these could be like planar slab waveguides, 2 of them put together. Right, so could be any waveguides. If we know the mode profiles, then we can calculate what these coupling coefficients are. Right, again, so in this case, we neglected, or we did the same step. So we neglected psi2 star psi1 integral compared to mod psi2 square. Okay, so we have these two equations now. For A and B, right? How A and B change with the amplitudes of the modes in the two fibers, how they change with distance. Kappa on wavelength. Right, so recall, so here, of course, wavelength directly is coming in K naught, right? K naught is 2 pi by lambda. It's also coming in beta, this propagation constant, which is 2 pi by lambda times n effective. N effective is also a function of lambda, recall. So, and in some sense, these mode profiles are also slight. I mean, we saw the confinement factor was also wavelength dependent. So, as you change for the given structure, as you change wavelength, these coefficients will change. But it's not very straightforward to see what the functional dependence would be. But you can see if they will increase or decrease, right? So basically, what is happening, right? You're calculating the cross terms here. So, for example, you know that as we increase wavelength, the confinement factor in the waveguide goes down, right? Which means that the mode leaks further out. So, which means this cross term, if this mode leaks further out into the other wave region of the other waveguide, then this cross term, the integral will have a larger value, right? So you can see that as you increase wavelength, the individual modes leak out more into the other region, and this coupling coefficient will go up. Right? So for the same structure, as you increase wavelength, these coupling coefficients will go up. Right. So sometimes these equations we can write in a simpler form also, you will see. So basically, if we define these new amplitudes with including the phase factors, like that. Okay, so basically, yeah, so plug in capital A in terms of small a into these and capital B in terms of small b into these equations, you can see that the equations will look like this. Okay. So now you can sort of more explicitly see, so this kappa 1, 1, the self terms are corrections to the propagation constant, right? So you can define this as a new propagation constant beta 1 prime, which is beta 1 plus kappa 1, 1. So basically, this coupling between the two waveguides is modifying the effective propagation constant in each waveguide, right? So, and this kappa 1 and kappa 2 are the corrections to the individual propagation, right? And then you have a cross coupling term. So A is coupled to B with this kappa 1 2 and B is coupled to A with this kappa 2. Okay, and again we already discussed, so this kappa 1 1 and kappa 2 2 typically will be small, right? Because we are talking about how much this goes into the other region here. So this correction will be small. So typically the magnitude of kappa 1 1, which is much smaller than beta 1, and similarly for 2. Right. So typically, in most cases, we can, especially in this weakly interacting condition that we already took, right? This correction is very small, so that you can assume to first order that the individual propagation constants haven't changed, right? And the main effect is happening just because of this coupling between the amplitudes in the two waveguides, right? So if we neglect kappa 1 1 and kappa 2 2, right, and again see the equation in terms of this capital A and B. Like you can even do that straight away here. Just neglect the kappa 1 1 term and the kappa 2 2 term here. Okay, so we end up with these simple coupled equations for any. So these are known as the coupled mode equations. Right, so the amplitudes in the waveguides A1 and 2, A and B, are coupled to each other, you can see, by these coupling coefficients kappa, which depend on sort of mode overlaps. Right, so we'll stop here and then, so we'll start from here in the next class and then solve for these amplitudes A and B to see actually how the power in each waveguide varies with propagation. Any questions? Yeah, oh, actually the next class is tomorrow because tomorrow, although it's Saturday, it's working as Friday timetable. So we'll have a class tomorrow. All right, no further questions, then okay. Slowly varying envelope approximation. Yeah, so recall there what we did was so we said that the second derivative of the amplitude is small in comparison to the first derivative multiplied by the propagation constant, right? So I can sort of write this as, so propagation constant, I can write as 2 pi by lambda times n, right? So n, so n is order of unity, right? So we know, like, for example, in optical fibers, n is around 1.5 or something, right? So forget about these constants for now. So basically what we are saying is that, right? So we take this to the other side. So now, so we are saying that the second derivative times lambda divided by the first derivative is much less than 1. Right, so what is this? So this is the change in slope, right? So this is like delta A, or this is like the change in dA over dz over one wavelength, right? So this is something like, you can see, it's like this, z plus lambda minus dA over dz, right? So I'm taking the second derivative, multiplying by lambda, right? So this gives me how much change is happening in dA by dz over a distance lambda, right? So this thing is basically giving me this. Right, and in the denominator I have just the magnitude of the slope. So you can see I'm seeing how much, what is the fractional change in the slope over one wavelength distance. Right, so if you can, so if I plot A of z, right, so I'm seeing how much the slope here is changing when I change z by one wavelength. Okay, so basically what we are saying is that this change is slow, so that the slope over one wavelength propagation distance is not changing much, right? So the fractional change in the slope is very small over one. So the variation is happening over distance is much larger than